You might not think it on a cloudy day like today, but we're here at the Rutherford Appleton Laboratories to seek out the sun. That's because the Rutherford Appleton Laboratories are our base of operations for solar physics in the UK. From here they conduct experiments on several spacecraft launched by NASA and the European Space Agency. Experiments that are helping us understand the origins of the solar wind, coronal mass ejections that cause solar storms, and gigantic flares that dwarf the Earth. Our eyes in the sky are SOHO, the Solar and Heliospheric Observatory, NASA's STEREO, a 3D imaging mission, the Japanese Hinode spacecraft, and the latest addition to this solar fleet, NASA's Solar Dynamics Observatory. But all of these missions have scientists working out of RAL. I'm here now with Professor Richard Harrison, who heads up the Space Physics Division here at RAL, and he works on several of the spacecraft that are currently observing the Sun. Can you tell us a little bit more about them? Because I think a lot of people probably don't realise that NASA-funded missions are conducted here.
Well, the NASA missions and ESA, European Space Agency missions, and even Japanese Space Agency missions. And we have different involvements in different ways. There's the Solar and Heliospheric Observatory, or SOHO for short, which is a European Space Agency mission with NASA involvement. We run our own instrument on that spacecraft. There's the NASA STEREO spacecraft, and we have an instrument aboard each of those two spacecraft, again, that we operate. And other missions that we either have involvement in through a particular instrument or providing part of a different instrument and scientific involvement and so on. So there's a huge spectrum in about actually 7 or 8 missions.
On the picture behind us, which I think was taken by the SOHO spacecraft,
that's right,
there's active regions and prominences and things, and they all result in a wind of charged particles that come out in our direction called the solar wind. Can you tell us a little bit about the origin of this solar wind, the mechanisms that create it, and how it affects Earth? Well,
the Sun isn't the smooth, featureless, inactive sphere that most people expect it to be. It's actually quite highly structured and complicated, and this image is taken in ultraviolet light. And in other forms of ultraviolet light, you can actually see a real complex atmosphere. It's actually made up of magnetic fields. It's those magnetic fields that are at the heart of just about everything. And if you home in on the Sun's atmosphere, like a microscope if you like, and some of the missions that we're involved with now are really doing that, like the SDO mission in particular maybe, you can see the fine scale structure in here. It's like elastic bands that are flowing around. And within that activity, there must be sites where particles are getting accelerated or heated to heat the Sun's atmosphere or to accelerate the solar wind. And we can think of various mechanisms that would do that, such as wave activity coming through those magnetic fields, driving particles out, or little explosions everywhere, accelerating particles out, little jets. If you like, there are lots of ideas, as many ideas as there are people probably, and we need to really pin that down. So that's the kind of thing we're all trying to do.
And how fast does the solar wind move?
Typically the solar wind's coming out maybe at a few hundred kilometres per second, but there are higher speed wind streams associated with the polar regions coming out the top and bottom of the Sun, if you like, which can get much faster than that, more like 700 kilometres per second. And the lower regions, down where the Earth is, if you like, this few hundred kilometre per second speed, it's more buffety, the environment that we live in, if you like.
And before people say, hang on a minute, there's no air in space, how can there be a wind? Can you just explain a little bit about exactly what the solar wind consists of and how it propagates through space?
Well, sitting out here at Earth, we have a flow of particles that come from the Sun, which expand outwards. By the time it gets to us, there might only be something like 10 particles per cubic centimetre or something like that. So you take a cube of sugar, you've got 10 particles in there. To all intents and purposes on Earth, that's a vacuum to us. And if you're trying to create a vacuum, you'd be pretty pleased with that. But having said that, that means space isn't empty. It does have that matter in it. And of course, if you think of something as big as the Earth, or huge clouds coming from the Sun, which might only have that sort of density, as they pass over us, they can still actually be quite significant, especially if they've got magnetic field attached to them. They're carrying out magnetic field and it hits our magnetic field and so on. So even though there's almost nothing there, we do care about it. It does matter, even though it looks like a vacuum.
So what are the repercussions when it does hit Earth's magnetic field?
Well, if we have one of these clouds coming through that the Sun's thrown out at us, the impact of its magnetic field and ours together, and the particles that might come with it and so on, can have a range of impacts on us. It can include disruption to navigation, communication systems, power distribution systems. You know, if you're an astronaut, you don't want to be bathed in energetic particles and so on and so forth. So there's a whole bunch of things. And people are often aware that there's been the odd blackout, for example, as a result of solar activity. But there's a whole catalogue of things like that, or the odd loss of a spacecraft or a spacecraft system and so on and so forth. And each of these has a price tag associated with it. So we want to be able to predict these things.
You're a co-investigator on the new Solar Dynamics Observatory that NASA launched just this February. And obviously that's going to be looking at very high resolution at the Sun. In terms of your own research that's carried out here at RAL, I mean, what kind of things are you hoping it will find?
Well, I think the first thing to say is that what we're trying to do more and more is use the different spacecraft that we have together. So in particular, the big clouds that are impacting the Earth that we see actually very well with the stereo spacecraft. And we can say an awful lot about the origin of these clouds using the SOHO spacecraft. The thing we need is a sort of extra resolution at the base to really understand how those magnetic systems begin to evolve in the first place, to develop in something that's complex enough to erupt from the Sun's atmosphere and come flying out in our direction. Then you've got the full story, if you like, from the beginning to the impact at the Earth. So it's a bit like a big jigsaw puzzle in that sense.
Okay. The secrets of the Sun are steadily being unlocked here at the Rutherford Appleton Laboratories. So there you have it. Every day here is a sunny one.